I will present a new tool which I have developed. This tool is for finding and fixing unused Python code. And my presentation consists out of 4 parts. First, I will introduce the state of code detection using existing tools. I will talk about my Deadcode package and its advantages. Third, I will show how to use practically that package, and finally, I will compare several code detection strategies. I think it would be good to start with a definition of what Deadcode is, because this term has a lot of different definitions. And I'll define Deadcode as unused and no longer needed code, which had to be removed, but it wasn't. And this type of unused code is actually a problem because it creates technical debt. It requires cognitive capacity to understand it. Also, it has to be maintained because whenever a dependency version or Python version is being upgraded, you have to update all your code base, including unused code. So that requires time. And also, unused code might use dependencies which might get outdated, and those outdated dependencies might have security vulnerabilities. So unused code might even increase security risks. And this unused code is like those Smith agents from Matrix, which are waiting to cause trouble for you. So we actually want to get rid of unused code. And removing unused code saves time, money, and reduces risks. And I have a story to tell. Once I have encountered a pull request which contained a really useful new feature. But that pull request also contained an unused class, which author wanted to use, but later decided not to use. But it was left in the code base. And I was shocked that this type of unused code was not detected by our linters because those linters were bleeding edge. We were using a rough with all linting rules enabled, and still this type of unused code slipped into our code base. And it would be excellent to detect and automatically remove such unused code occurrences. So this led me to an investigation why RUF was not able to detect this type of unused code. I have looked into those 700 linting rules and found that regarding unused code, there are only several rules, and they are only for local unused code, basically for local variables and unused imports. And this is only a really tiny fraction of all unused code which might exist in a code base. So RUF is not capable to detect such cases yet. And I searched for other tools and found that Vultr is the most popular and capable linter which deals with such kind of unused code cases. This package has over 3,000 GitHub stars, so it's pretty old and popular, and I tried using it, but I have faced several issues. And let's consider this example. We have a class with several attributes, and this class has a subclass called meta, and this meta class is only used for configuration. So Vultr detected a lot of false positives in this case. It provided each attribute as a finding of unused code. And for larger code base, it is very time consuming and inconvenient to list all those false positives case by case. If I wanted to add a new attribute, I would have to add its name to Vultr configuration. So that's really time consuming and inconvenient, and there is no way to tune out those false positives. Well, this made Vultr unusable in my case. And also another huge disadvantage is that you have to remove unused code items manually. Vultr is only capable to find them, report them, and you have to fix them yourself manually. So this led me to creation of new package. And I have decided to create a new tool for Deadcode detection because, well, initially I looked into Vultr's code base and decided that it would require 2 significant refactoring to implement features which I need, and that's why I decided to create a new tool, not to improve the existing one. And Deadcode is implemented in Python, but I think eventually it might be re-implemented in Rust and might be integrated, re-implemented in Rust and integrated in Rust if it gets recognized. Comparing this Deadcode package with Vultr, I see 3 main advantages why Deadcode is better, and these 3 advantages are like, first of all, Deadcode provides way more options to tune out false positives. It's more flexible. Second advantage is that it is able to find more cases of unused code, and finally it provides automatic fixing feature, which allows to automatically remove all the findings without doing any manual job. Let's look into these features in more detail. So first feature which allows to tune out false positives is implemented by adding more options which allow to ignore code in different ways. I have used 3 terms to identify what has to be ignored, and these terms are name, body, and definition. And you can see in this example, those code parts are marked accordingly. So by providing a name, you can choose what you want to ignore. A single name, a body, or a whole definition. So that adds a lot of flexibility. You don't have to specify name each time you have a new occurrence of unused code. And in addition to a way to ignore code by name, body, or definition, those options also allow to ignore code based on usage. So you can specify a base class for which all child classes have to be ignored, or you can specify a decorator with which code item is decorated, and based on that, code might be filtered out. Looking into this example, we can see that a single entry ignore definitions method allows to completely ignore all meta classes. And we don't have to list options explicitly anymore. And this applies for decorators and base classes. Another advantage is that Deadcode provides more types of checks, and all of these checks might be ignored per line or per file, as provided in these examples. Those checks are mostly similar to Vulture's checks. A couple additional were added, and those are for empty Python files and unreachable code, as well as commented out code. And the last advantage is automatic fixing. And it is pretty convenient to automatically fix code, but sometimes we want to make sure that this code is being removed correctly, and we can see that by using additional dry flag. And also another interesting feature is that sometimes Deadcode might want to remove all content of a file, and in such cases Deadcode will remove the file itself, unless it is a special file which is named using dunder name. Yeah, so let's see how this package might be used. It's pretty straightforward. You have to just run pip install Deadcode, and you are ready to use it. So after installation, you have to run a CLI command called Deadcode and provide a list of files which have to be checked. If you want to check all Python files in a current directory, you can use a simple dot. But let's consider this single file. We have a Python file called foo.py, and it contains a lot of unused code entries. And those entries are highlighted in purple. So when you run Deadcode foo.py, you get a list of unused code entries. And if you want, you can automatically fix them by using -fix option. And in this case, we see that the same list of findings is provided, but we get an additional node at the end that those code items were automatically removed. And here is a resulting file which we get after running this automatic checking. And we see that it was pretty convenient to get all those unused entries removed automatically. Yeah, it is really important to highlight that we have to tune out all false positives before using automatic code removal, because a good working code might suffer. So we should first make sure that Deadcode configuration is correct and findings are valid, and only then we have to run that automatic fixing command. And let's move to the last part. Let's compare different strategies of detecting unused code. And to begin with, I would like to highlight that detecting unused code is a really complex task because there is no way to associate code definition with its usage. Both Vultr and Deadcode packages are using abstract syntax tree to kind of partially parse Python files, but the result is only a tree of names, and there is no easy way to associate definition, defining names with places where those names are being used. So even though the input for those two tools is the same, the strategy applied is slightly different. Let's consider this simple example, and let's see what Vultr does for this example. So first, we have a class which has a single method, and Vultr will find all defined names. So these are foo and method spam. Then Vultr will find all names which are being used, and those are again foo and spam. And as a last step, it will record all defined names which were not used. In this case, we end up with an empty set. So nothing will be reported. But let's complicate this example a little bit by adding additional class called bar, which has a method with the same name. So in this case, the Vultr will first find all defined names, foo, spam, and bar, find all used names, foo, spam, and bar, and will record all defined names which are not used, which is an empty set because spam method was used once, but Vultr does not track namespace of those methods. So single usage will mark both spam definitions as used. So bar spam method won't be reported even though it should be. And let's consider a different strategy by Deadcode. And Deadcode uses dot-separated paths to track namespaces where code items are being used. And as a first step, Deadcode will find defined names, and in this case, spam method will have two occurrences. we will have foo.spam and bar.spam. So those are two different definitions. And as a second step, we will detect that foo spam method is being used, but no entry for bar.spam. And as a last step, we will find that bar spam was defined but not used. So in this case, Deadcode will find this code occurrence correctly, but it is important to know that it is really hard to track the type of the variable which is being used, because this variable might be passed into different contexts, and sometimes dot separated namespace is being lost. So Deadcode will fall back to Vulture's strategy and will not report that finding if a single usage is being found. So we came to a conclusion that Deadcode package prevents technical debt from appearing out of unused code. So this should save time, money, and reduce some risks. Thank you for listening. And do you have any questions?
We had one question in the chat. Do you like to ask?
Yeah, I'd like to ask. So I'm sure this works really fast on small code bases, but what about big ones? Like, what's the performance attributes of Deadcode versus, say, Vulture?
So I don't have those measurements because this package is pretty new, and I'm pretty sure that Vulture is working way faster for large code bases, but from practical applications, I saw that code bases which have hundreds of files are being handled instantly, like in under a second. So that didn't cause any issues for me.